Hello and welcome back to COMP31619164. Today we're going to be looking at some of the mathematical techniques that we'll be using in the course, specifically induction. So I assume that most of you in discrete mathematics or in high school or in other areas have seen some form of induction before, but probably the induction that you've seen so far was just induction on natural numbers. We're going to extend that notion of induction a little bit today to talk about structural induction, which is induction over mathematical structures in general. And to motivate that, I'm going to be using Haskell. So what we'll do is we'll write functions in Haskell and data types in Haskell and prove properties about them using induction. And if you've done COMP3161, you would have done a little bit of this already, but this lecture will extend on that stuff a little bit further than 3141 does, so stay tuned for that. So firstly, let's recap what we know, or what we probably know, about induction from other courses. So if we wanted to prove a property P, which is a predicate, that is, it takes in a natural number and returns true or false. So if we have such a predicate, and we want to show that it holds for all possible natural numbers x, then we can use induction to show that. And the reason we can use induction is because natural numbers are an inductive set. That means they're defined in an inductive way. So any inductive set has axioms which build in the basic elements of the inductive set. So in the case of natural numbers, we have 0. And they have production rules that tell us how to create more elements of a set based on existing elements. And in the case of natural numbers, we can do that with adding 1. Right? So if I say that I want to define natural numbers, the easiest way to do so is to say 0 is a natural number, and if I pick any other natural number and add 1 to it, I get another natural number. And this inductively defines all natural numbers. So because natural numbers have this inductive set definition, we can prove any property for all natural numbers by saying, if I can prove it for 0, so if I show my property P for 0, and I also show my property P for k plus 1, assuming my property holds for k, then I've shown it true for all natural numbers. Because any natural number can be expressed as 0 plus 1 plus 1 plus 1 however many times. So this assumption, P of k, that I make when I'm trying to show P of k plus 1, that's called the inductive hypothesis. And so we have these base cases where we don't have any inductive hypothesis and they're based on the basic elements of our inductive set. And then the production rules give us this inductive case with an inductive hypothesis for each of the smaller pieces. So let's do an example just to jog your memory on how we do induction. Firstly, we're going to write some Haskell program which adds up all of the numbers from 0 to the input number n. And I'll write this recursive function on the iPad using my handwriting. So I know some people dislike writing code, like handwriting code, but it doesn't bother me. And I think it's kind of nice to do this for reasoning about Haskell. You can, of course, type this up in your editor if you like and run it. But today we're going to be proving things about Haskell, not running them. Okay, so let's write this recursive function. Let me just switch over to the iPad. Here we go. So the function that we're going to write is called sum2, and it takes in an integer input. Integer supports negative numbers, but today we're not interested in those. So we take in our integer input and produce an integer output. And whenever we write a inductive or recursive function, same thing, then we need to think about our base case and our inductive case. So in the base case, Well, the base case is clearly 0. The sum 2 of natural numbers from 0 up to n, well, the base case is the sum of natural numbers from 0 up to 0, and that's just 0. Now, for our inductive case, normally you would think of sum 2 of n plus 1, right? Or sum 2 of k plus 1. But in Haskell, we don't really write that. We just would say sum 2 of n. And because Haskell always applies the equations in order, it will always apply equation 1 before it applies equation 2. So that tells me that if I am running in equation 2, then equation 1 doesn't work. So that tells me that n cannot be 0, because if n were 0, it would have run equation 1 instead. So that means that I know that n is non-zero, and for the sake of convenience, we're assuming we don't have a negative input. So that means that I can just write my inductive case here, n plus sum 2 of n minus 1. So we subtract 1 there. Okay. So, if you've done certain math courses, you probably will know that sum 2 can be written without recursion at all. So what we want to prove today is our property P of natural numbers n is going to be defined to be sum 2 of n equals, I believe it's n times n plus 1 over 2. I believe that is the correct closed form. Sometimes I think it's minus 1, but I think that's if you do not include the upper bound. But we are including it today, so it's n times n plus 1 over 2. But anyway, if I got it wrong, we'll certainly see that when we try and do the proof of this property here. So what we're going to do is apply the schema that we saw in the slides. First, we need to show P of 0, our base case. So our base case, when n is equal to 0, we need to show that sum 2 of 0 equals some stuff, which hopefully eventually will equal 0 times 0 plus 1 over 2. And, well, looking at equation 1 here, it's pretty clear that sum 2 0 equals 0 by equation 1, and then that's clearly true by maths. So we've completed our base case. So now let's do the inductive case. This is when n is going to be some k plus 1. And now we have to show our property for k plus 1, but we get an additional assumption, our inductive hypothesis. Now normally I'm not going to bother writing inductive hypothesis like that. Instead I'll just write IH, which is going to be, in this case, it's always what you want to show, but for the smaller number. So in this case, it's going to be for k. So we want to show sum 2, we assume as our inductive hypothesis, sum 2 of k equals k times k plus 1 over 2. And what do we have to show? Well, we have to show that sum 2 of k plus 1 equals k plus 1. Oh, I should leave some space to do some working, so let's go down here. K plus 1 times k plus 2, which is k plus 1 over 2. Okay, let's see what we can do about that. Let's first write sum 2 k plus 1 using our second equation. And we can apply the second equation here because we know that the first equation doesn't apply because we've got this plus 1 here. and we're assuming we're not dealing with negative numbers. So we have sum2 of, sorry, I miswrote that down. It should be k plus 1, which is our n in equation 2 here, plus sum2 of k plus 1 minus 1, which is just k, like that. So that was via equation 2. Next, if we look here, we can see that our inductive hypothesis can apply, because we have this sum2k term, and our inductive hypothesis is about sum2k. So let's rewrite that. So we get k plus 1 plus k times k plus 1 over 2. And now let's get that all under the same denominator. So we get, let me write it like this instead, just to make it a bit cleaner. So we can say 2k plus 2 plus k times k plus 1, like that, times a half. And that is just getting them all under the same denominator. And now we can multiply out the k plus 1. So we get half times 2k plus 2 plus k squared plus k, which is equal to half times k squared plus 3k plus 2. And if you expand out the top level, the part on top of the fraction there, you'll end up with the same formula. So all of these steps is just mathematical manipulation. So that completes the proof, because by showing it for the case where n equals 0, and then showing it for the case where n is k plus 1 for any natural number k, assuming our property for k, we have shown it true for all natural numbers. So this property holds. So it looks like I got the plus 1s and minus 1s around the right way this time. Very good. Okay, let's go back to the slides. So we just proved this property. So now let's try and define natural numbers inside Haskell ourselves. So I said before that natural numbers have this structural definition, this inductive definition, and we can reflect that by defining natural numbers as our own data type. So we can say, sorry, just having a drink of water, that natural numbers here are either 0, right, which we write as z, or the successor of another natural number. The successor means plus 1. So, for example, the number 3 would be written as successor of successor of successor of 0, right? So it's an inefficient way to write natural numbers, but actually, if you look at any foundational mathematics textbook or the implementation of any theorem prover, this is indeed how they define natural numbers. It's how we define natural numbers when we're talking about the primitive structures that make up our mathematics. So, to show you what I mean, I'm going to define something as simple as addition in terms of this data type. So let me just switch back to the iPad. Okay. So what we're going to do now is we've got our data type definition. Let me just write it down again. So it's data, a natural number is either 0 or the successor of another natural number. Okay? So now what we want to do is write our own addition function, which we'll write like this. So plus is an operator that takes in a natural number and another natural number and returns me a new natural number, right? Or alternatively, we can read this as plus is the function that takes in a natural number and returns to me a function that takes in another natural number, and then that returns a natural number. Remember, these parentheses that I'm putting in dotted here are optional, and it is equivalent to put them in or leave them out. Haskell functions always take in one argument and return, if they need to take more arguments, a function to take in the remaining arguments. Okay, so let's implement this. So as with any function that works on an inductive data type, we want to have a recursive structure. So firstly, we'll deal with our base case, and we can pick either side of either one of the two natural number inputs to be our the input that we do recursion on. But for the sake of sticking to the mathematical convention that already exists, we'll do recursion on the left-hand input. So if we have 0 plus, kind of looks like a 2, so I'll just put a dash between it to make it clear that that's a z, not a 2. So 0 plus some natural number n, and successor of m plus that natural number n, and now we have our two cases. So we don't have a case here for n plus 0. We don't need one, because we've dealt with the case where the left-hand side is 0. We dealt with the case where the left-hand side is successor. So that means these two equations together cover all possible inputs, and I don't need to have any further equations to cover any other cases. Okay, so we don't need an n plus z equation. We just need a z plus n and successor plus n. So what is 0 plus n? Well, it's just n, right? So we just return n here. And what is successor of m plus n? Well, it's the successor of m plus n, which that sounds like exactly what I just said, but the bracketing is different, right? So in order to have a valid recursive function, we want the input to consistently get smaller so that it goes down and down and down until it hits a base case. So what we want to do is recursively call plus on m. So we'll say it's the successor of m plus n. Okay? These recursive functions can be a little funny at first, but it will sink in eventually, don't worry. So we have this recursive definition of addition, and this is in fact how addition is defined. And so this is where we get to doing some proofs. So let's prove the blatantly obvious fact. So the property that we're going to prove today, p of natural number n, is that n plus 0 equals n. So you might think, oh, don't we already have that from this first equation here? But no, we don't, because the first equation said 0 plus n, and this equation says n plus 0. So we know, just from our knowledge of addition, that addition is commutative, and therefore if 0 plus n equals n, then n plus 0 equals n. But that isn't immediately obvious from our definition, so you'd have to prove that as a separate theorem. We haven't proven that our addition definition here is commutative, right? So what I want to do is prove that n plus 0 equals n. And I'm going to do that by induction on n. So we have a base case and an inductive case, just like before. Base case. And here, our n in our p of n here is going to be 0. And now I'm using the notation for the data type, because this is the data type that I'm doing induction on now, not just our general notion of natural numbers. So now I need to show 0 plus 0 equals 0. Well, that's easy, because now that is indeed an instance of equation 1. So that's the base case, easily handled. So now we have an inductive case, where n is equal to the successor of k. I didn't say k plus 1 because now we're doing induction on the data type. So we have our inductive hypothesis here that says that our property holds for k. So we know that k plus 0 equals k. And now we need to show that successor of k plus 0 equals some stuff which equals k, which equals successor of k. And what does successor of k plus 0 equal? Well, we can see that the first equation for plus doesn't apply, but the second equation does. So we can use the second equation here, and we're going to get successor of k plus 0. And then, in order to get to successor of k, I can just use my inductive hypothesis, because I can see this k plus 0 term here. So if I use my inductive hypothesis, I get to successor of k. And that's the proof. So now we prove the very blatantly obvious fact that n plus 0 equals n. You can continue to do a bunch of proofs like this, and you can end up with a proof that, say, 1 plus 1 equals 2, right? It actually requires a fair bit of mathematical machinery to generalize these proofs and prove these basic properties of addition that we know intuitively. But this is indeed how it is done. So now we know how we define these basic concepts. Let's move on to some more interesting data types. So the thing to observe here is that the structure of our induction corresponded exactly to the structure of our data type. We had a base case for these base case constructors that don't recursively refer to themselves. So 0 is a base case constructor. It doesn't refer to nat in anywhere. So it corresponds to a base case. And then successor, which recursively refers to nat, corresponds to an inductive case. And this is a hint that we have an inductive structure here. Now, it's possible to define weird data types in Haskell that do not have inductive structure, but for most normal data types, they do. If there's time and we have a bit of an extension period at some point, maybe I can talk about those data types that are non-inductive in Haskell. But for now, let's just assume that all our data types are inductive. So the next data type I want to look at is a list. So as I mentioned in the last video, briefly, the lists in Haskell are basically singly linked lists. So if we have the string hi here, as I said before, strings are just lists of characters. So we have a character h in a list, followed by I, followed by exclamation mark. And these lists are essentially recursive structures. We have a list node, which we write with the colon, and you pronounce that colon as cons, C-O-N-S. It's just a historical name for it. So we say h cons, I cons, exclamation mark cons, nil, the empty list. So what's going on here is we have this recursive structure where on the left-hand side we have a value that goes inside our list, and on the right-hand side we have another list, right? So this is this recursion that's going on here. And you can write that without the parentheses, and the associativity works out the same way. So what we're going to do now is define some list functions. So we're going to define 3 list functions. All 3 list functions already exist in the standard library, but we're going to define them ourselves for practice. So let's go to the board, and I would like to have some lines, please. Okay, so the first function that we're going to write is just to get the length of a list, right? And its type is simple enough. It's just a list of any type A. It doesn't matter what type it is. and it will return to me an integer. So length. Now we have a base case and an inductive case once again. So the base case is going to be the empty list. And the length of the empty list is of course 0. And then the inductive case is the cons cell, or the node. So we have a value, which historically we've always written as x, and then the rest of the list after the cons cell, which is just x's, right? The rest of the x's. Okay, and the length of this is just the length of x's plus 1, right? So there's our definition of length. Okay, now we will define a slightly more interesting function. It's called take. And take takes in an integer, the number of elements to take out of a list of A's, and gives me back a list of A's. So take, if I am taking n from an empty list, well, there's no more elements that I can possibly return. So I just have to return the empty list. I'm stuck there. And if I take 0 elements from some list x's, then I also return the empty list, because if I'm asking for 0 elements, then I can always give that. I don't even need to look at the list I'm given. And then otherwise, I know that my list is a cons cell because I already checked if it was empty. And I also know that my number n here is not 0. So what I'll do is I will first return x, because I know this is going to be the start of my list. And then the rest of it is take n minus 1 of x's. Okay. Now, to save a little bit of space, I'm going to just nudge this over slightly, because I want to squeeze in one more function up the top here. And that extra function is called, oops, it's not called whoops, it's called drop. Now drop is going to be really similar to take, has the same type signature, taking in a list of A's and a list of A's, but it sort of does the opposite thing. Where take returns the prefix of length n, drop returns the suffix after the first n elements. So if I drop n from the empty list, that's still the empty list, there's nothing I can do there. If I'm told to drop 0 elements from a list x's, then unlike take, it's going to return all of the rest of the list because I'm not dropping anything from it. And then if I drop n elements from a non-empty list, and this n is non-zero, then it's just drop n minus 1 elements from x's. Okay, so there's our 3 functions. So now how can we reason about lists in an inductive way? Well, as I mentioned in the last lecture, we could have defined lists ourselves with slightly different syntax just by writing a data type definition. We'd say there's a constructor called nil, which just makes a list of anything. It doesn't require any arguments. And it's the empty list, right? And then we have this cons cell that has a value and another list, which is the tail, the rest of the list. So this is our definition. So this gives us a hint as to how we do induction on lists. We have a base case for this non-recursive case here, and an inductive case for this recursive one. So if we want to prove a proposition holds, so our proposition is P of x's, or the predicate is P, for all lists x's, then we need to show it true for the empty list, right? Which is our nil constructor there. And we need to assume that it's true for some list x's and show it's true if I put a new element on the front, right? For the cons case. This is from cons. So this strongly resembles the induction that we've done on natural numbers, but now instead of natural numbers, we're doing lists. So let's do some example proofs. So the first one I want to show is that if I take the length of x's from x's, then I get back x's. Should be straightforward enough. I want to show p of x's, which is take the length of x's from x's. And then that should just be the same as x's, right? Doesn't require too much of reasoning to see that intuitively. So let's do the base case first. Base case. So in our base case, we know that our x's is going to be the empty list. And we want to show that take length of the empty list equals the empty list. And this is easy because it's just an instance of the first equation of take, which I'll write a 1 next to, so it's 1, and that's it. Now we didn't need to worry about length empty or whether or not it was 0. It doesn't matter because this take equation always works, right? We can just apply equation 1, because if I had swapped around these two equations, then I would have to worry about whether or not length of the empty list is 0. But because the very first equation for take doesn't care what the length is, so long as the the right hand argument is empty list, then we can just straight away use that equation. Okay, so that's the base case. Now let's do the inductive case. Where x's is equal to x followed by, let's call it k to save confusion, k followed by k's, and our inductive hypothesis, which I forgot to abbreviate as IH, is take length of k's from k's, and then we need to show that's equal to k's. So this is essentially what we want to show, but for the smaller list. And now I need to show that take length of k followed by k's of k followed by k's equals k followed by k's. Right? That's what I need to show. So let's try and get there. So we can't straight away we definitely can't use the first equation of take. Can we use the second equation of take? Doesn't look like it. Why not? Because if I evaluate using this is A and this is B here. So if I use equation B, then I can see that this is take 1 plus the length of k's, of k followed by k's. And because we've got that 1 plus there, and it's pretty obvious to see that length doesn't go negative, so that tells me that the first argument to take here is not 0. So we can't use equation 2, the second equation of take, either. So we can use equation 3. So we ruled out equation 1 and 2, so now we can use equation 3. And that gives us take whoops, sorry, no, I forgot. It's k followed by take length k's of k's. And if we can, so this was equation 2. And then if we look at our inductive hypothesis, that's equal to k followed by k's, which is what we wanted. Okay. So that's our proof of that first property. So now I want to show that if I take 5 elements from a list X's and then drop 5 elements from a list X's and then concatenate those two lists that I get back together, then I should get my original list X's back. Now I haven't given you a formal definition of the plus plus function. That will be the topic of, well, one of the topics that you'll cover in the tute. So I will informally describe plus plus for now. We know it as basically just the function that appends two lists. So it's going to take the first list and the second list and replace the nil in the first list with the second list, giving us a connected list together. So let's do some proofs about that, or try to anyway. So I'll give you a warning here that what we're going to do here is get stuck, and I'll teach you afterwards how we can get unstuck. So firstly, I just need to copy paste the definitions that we just wrote down. So it's just not cooperating with me just yet, so give me a moment. Hold on. Okay, one last try and then I'll just give up. There we go. Okay, got it. So now I'll go back to the iPad and we can switch to a new page. And I can put these definitions back in. X's there. Okay, so now we still have our functions from before, and what we want to try to show is our new property P of X's is take 5 X's plus plus drop 5 X's equals X's. So let's try to prove this. Base case is when X's equals the empty list. Well, that's easy enough to prove, because if I take 5 of the empty list plus plus drop 5 of the empty list, that's just the empty list from the first equation of take plus the empty list, which is the first equation of drop, which is pretty clearly, hopefully, equal to the empty list. So that's easy enough. But then, in my inductive case, well, X's is going to be k followed by k's, and I'm going to have an inductive hypothesis that take 5 of k's plus plus drop 5 of k's equals k's. That's my inductive hypothesis. And what I want to show is take 5 of k followed by k's plus plus drop 5 of k followed by k's equals, eventually, somehow I need to get to k followed by k's. So if I try to simplify this using the equations that I have, then I end up with this unfortunate mess. I get k followed by take 4 of k's plus drop 4 of k's. And there's no way to get to my conclusion from here. My inductive hypothesis is talking about 5, not 4. And even if I use some associativity property about plus plus and cons here, it's not going to be enough, because this term here, take 4k's plus drop 4k's, is about 4, not 5. So my inductive hypothesis and what I want to show don't line up. So when you see this problem, this means that the thing that you're trying to prove is too specific. And what you need to do is generalize what you're trying to show, which makes it easier to prove because you get a stronger inductive hypothesis. And if you prove a more general property, then you can then instantiate that property to prove the specific property you want. So the thing that was unfortunately too specific and prevented us from solving this problem was this number 5. So what I'm going to do is just briefly, I'm going to try and duplicate that. There we go. And in this duplicated version, I'm going to just creatively erase bits of it. And instead of 5, what I'm going to do is my property is now, actually I will erase a bit more just to make it very clear. My property is now for all n, take n of x's and drop n of x's, right? So this is now for all n, take n of empty list, drop n of empty list. And here, my inductive hypothesis is for all n, take n of x's, drop n of x's, of k's, sorry. And now I need to show for all n, take n, drop n, take n, drop n. So that may not have, whoops, sorry, that's a mistake. That should say n minus 1 here. In fact, I will rewrite this to make it very clear. I'll just rub that out and rewrite it. So we have k followed by take n minus 1 of k's plus plus drop n minus 1 of k's. And I'll use this implied associativity property here to rearrange the brackets. So this is actually take n minus 1 of k's plus plus drop n minus 1 of k's. I can move that k out based on the definition of plus plus, but you'll see how you can do that in the tute. So we have now got this term here, and so this was my associativity, this was the definitions, and now how do I get from there to my third step? Well, I was actually using my inductive hypothesis. Now, it doesn't quite immediately look obvious that I can use my inductive hypothesis here. After all, these terms are all about n minus 1, and it looks like my inductive hypothesis is about the term n. But you've got to pay attention to these quantifiers. We have for all n here, so that means the n that is being referred to in the inductive hypothesis is just any arbitrary n. And it's not the same n necessarily as the n that I have here, right? The n that I'm using in my proof. So I can instantiate the n in my inductive hypothesis to n minus 1, where n here is the n in my proof. I know it's kind of confusing to have multiple different variables with the same name, so you could even rename them. So I could rename the n in my inductive hypothesis. It's fine to rename variables if you want, so I can call this for all z, take z, and drop z, and then it's clearer what I'm doing here is instantiating that z variable to n minus 1, right? And that allows me to use my inductive hypothesis to replace that take plus plus drop with k's. And there we go. And that completes the proof. Okay, so let's go back to the slides. So this tells us that sometimes we have to generalize our proof goal in order to get a strong enough inductive hypothesis to complete the proof. And sometimes, although not in this particular example, it helps to prove a separate theorem, which we call a lemma, which is just another thing that we should prove first before going on to prove our main goal. And later on in the course, we'll see some examples where that becomes handy as well. So sometimes we can't just discharge a proof just by doing one induction and one and done. Instead, we might either have to generalize our goal, like we did here, or we might have to prove additional facts before we get to the facts at hand. In fact, to make the proof that I just did here completely formal, I should first prove that the associativity property that I just used here actually holds. And that associativity property, just to make it very clear, what I'm assuming here is this theorem, k followed by x's plus plus y's, sorry, that was my computer making a noise, is equivalent to k followed by x's plus plus y's, right? This was the theorem that I just assumed, and in order to really make this proof formal, I would have to prove that fact first as a lemma, right? So that's what I mean by sometimes you need to prove a lemma as well, and sometimes you need to generalize your goal, sometimes even both. All right. I'm just going to have a short break, and I will be back momentarily from your perspective, but in 5 minutes from my perspective. So be back in a moment. Okay, welcome back everyone. So I hope you've all had a drink of water and have refreshed yourself for the next half of the lecture. So in the next half, we're going to be looking at some more sophisticated induction. So far, all of the induction that we've done up to this point has also been covered in other courses, specifically in COMP3161 at least, but also potentially in other courses. So what we're about to do goes a little bit beyond that, and it gets a little bit trickier. So keep your thinking caps on, and feel free to ask us questions if you get stuck or get confused. And don't panic if it's a little bit complicated at first. We'll give you plenty of exercises when we introduce the other proof methods that we'll be doing in the next lecture. Next week we'll be giving you lots of exercises you can use to help work through and figure stuff out. So don't panic if it's a bit unapproachable at first, but make sure you work on it and let it sink in. Okay, so binary trees. So we've all seen binary trees before, I hope, in like our data structures courses. And so the way a Haskell definition of binary trees looks is similar to our definition of lists, right? We have a tree of elements of type A, which can be anything. It could be int or bool or car or whatever. So we could have a tree of anything, even a tree of trees if we like. And a tree can either be a leaf, which has no parameters, it's just an empty tree, or a branch, which contains a value, which is like our integer or whatever data we want to include in our tree, and a left subtree and a right subtree. Okay, so this is our definition. So as we've seen before, we've got a base case here from our leaf constructor and inductive case from our branch constructor. So let's see how that looks. So I want to prove a property P of all trees T. So then I have a base case from my leaf constructor, and then for the branch constructor, it looks a little bit different to what we did before. I assume two inductive hypotheses, one for the left subtree and one for the right. So I assume my property holds for both L and R, and then I show that it holds for branch XLR, where X is just some value, right? Any arbitrary value. So we have to show P of branch XLR, assuming that the property holds for L and R. So we get two inductive hypotheses here. And that's because tree is mentioned twice recursively in the definition of branch. So now let's do some proofs about trees. So that's another page here. Let's also get some lines here. I realized I forgot to put in lines for some of these other pages, but that's okay. Okay, and firstly we want to write a function called leave. Oops, wrong tool. There we go. We want to write a function called leaves. Apologies for my poor handwriting. I assure you my handwriting is normally much better. I'm just writing on an iPad, and my iPad handwriting is a lot worse than my paper handwriting. So we have this leaves function, which takes in an integer and returns, sorry, it doesn't take in an integer. What am I talking about? It takes in a tree of any type A and returns an integer, the number of leaves in it. So if we recall our definition of binary trees, I'll just quickly flick back to the sides, we can see we've got two cases that we're going to have to write, one for leaf and one for branch. So let's write the leaf case. So the number of leaves in leaf is, well, clearly it's just going to be 1, right? There is 1 leaf in leaves. Sorry, the number of leaves in leaf is 1, right? And how many leaves are there in a branch with a value x, a subtree L, and a subtree R? Well, a branch itself is not a leaf, right? So the only place that a leaf could occur is either in the left subtree or in the right subtree. So it's just the sum of the number of leaves in the left subtree plus the number of leaves in the right subtree. Apologies for terrible handwriting, but what other word could that possibly be, right? Okay, and now we want to define a function called height. And height takes in a tree of A's and returns an integer, so it's got the same type as leaves. But the height of a leaf is different. Oh, well, my spelling seemed to have deteriorated there. There we go. The height of a leaf is just 0 because leaf stands for the empty tree. So height of leaf is 0 and height of branch XLR is, well, each layer of a branch adds 1 to the height, so we'll have 1 plus. Actually, I'll write it on a new line. So this is 1 plus, and then it depends on the height of the children. So it's going to be some relationship between the height of the left subtree and the height of the right subtree, and if we look at it, it's just the maximum. In Haskell, you just use the max function for that. Okay, so this is the definition of height, definition of leaves. So now what we want to prove today, our property of trees that we want to prove is, for all trees, we want to show that the height of a tree T is less than leaves of a tree T. So this proof requires a few mathematical facts that I'm going to gloss over, but if you want to challenge me on any of them, feel free to try your hand at a proof. And if you don't believe me and you can't come up with a proof, then ask on Piazza and I'll give you a bit more detail. But let's proceed by applying our inductive scheme. So firstly, we have a base case, and our base case is going to be when T is a leaf. We have leaves of a leaf should be, sorry, not leaves, let me just rewrite that. It should be height of a leaf should be less than leaves of a leaf. And if we look at the definitions, that's clear. We get 0 and 1, and I'm pretty sure all of you will agree that 0 is less than 1. So that's an easy case to show. Now we have the inductive case. And we want to show that when T is a branch containing a value x, a left and a right subtree, and we get two inductive hypotheses, IH1, IH2, one for the left subtree and one for the right. And they both look very similar. One is that the height of the left subtree is less than the leaves of the left subtree, and the height of the right subtree is less than the height, sorry, the leaves. It's less than the leaves of the right subtree. Okay. So now, with these two inductive hypotheses, what we need to show is that the height of branch XLR is less than, ultimately, the leaves of branch XLR. And I'll just quickly do some expansion of the definition. So we get height of a branch is 1 plus the maximum of the height of L and the height of R. And leaves of branch XLR is leaves of L plus leaves of R. So now we need to show that this top part is less than the bottom part. So if we tried to use any one of our inductive hypotheses individually, we wouldn't get very far. If I tried to use the fact that I know height is less than leaves for the left, so like if A is less than B, then max A and some other number Z is not necessarily less than max B and some number Z. It's not a congruence in that way. We can't make this kind of judgment. So we can't just apply one of these inductive hypotheses. We can't go inside maximum and just say, yeah, well, because the height is less than the leaves, then this is less than, we can't then just say this is less than 1 plus the maximum of leaves of L, say, and height of R using IH1, right? You can't do that. That doesn't make any sense because maximum doesn't obey that kind of law. However, it does obey a more useful law. If I have four numbers, A, B, X, and Y, and I know that A is less than X and B is less than Y, then the maximum of these two, right, is going to be smaller than the maximum of these two. Right, so if I use both inductive hypotheses at once, then I do get this fact. I know this is smaller than the maximum of the leaves of L and the leaves of R. Now, if you don't believe me about this fact, try it out, convince yourself, or even ask Isabel, right? You can find out, you can prove this to yourself if you're not satisfied, but effectively the argument works by saying the maximum of A and B is one of either A or B, and similarly X and Y, and it's the biggest of the two. So if B is less than Y, and let's say B was the maximum, then that means that the maximum of X and Y is surely bigger than B. And if A was the maximum, then and X is greater than A, then the maximum of X and Y is surely greater than A, right? So the maximum is always greater. The maximum of two numbers is always greater if you have the maximum, the less than or equal to operator for each of the components. Okay, so the next step is to try and get somewhere closer to the sum, right? So we've gotten rid of height and we've shifted over to leaves using our inductive hypotheses. This is using the inductive hypotheses along with this fact. Then the next step is to try and relate maximum and sum. So one thing that we can note about leaves here is that leaves is always the sum of other leaves, or 1. So that tells me, I could even prove this inductively if I really wanted to, but I'm just going to hand wave this part of the proof. Leaves of t, for any t, leaves of t is greater than or equal to 1, right? And that's a pretty straightforward proof to see. So because of that, the maximum of two leaves values, the smallest this value could be is 1, right? Because leaves of L could be 1, leaves of R could be 1, and therefore maximum of those two would be 1. That's the smallest this could get. Whereas the smallest the sum could get, well, leaves of L could be 1, leaves of R could be 1, and then that would be 2, right? And so because of that, we can see that the maximum of these two numbers is always going to be strictly smaller than the sum of these two numbers because they're always greater than or equal to 1. So that's a little bit of a hand wave, but you can prove this formally in your own time if you do not believe me. But we have this property now that this is strictly smaller than leaves of L plus leaves of R. But we don't actually, we want to get rid of this 1 plus, right? So if I were to then subtract 1 from this, then I would no longer have the guarantee that it's strictly less than, So I would change this to less than or equal to and get rid of the 1 plus. And now I have something that I know from this reasoning down here at the bottom equals my goal. So what I'll do is I'll rewrite it. This is equal to leaves of branch XLR. Now, if you take all of this transitively together, then you have height is equal to 1 plus max, which is less than 1 plus max, which is less than or equal to leaves plus leaves, which is equal to leaves. So because it's equal to, less than or equal to, and equal to, taking all of these together, actually I'll write it this way, taking all of these together, we get this is less than, right? So height is less than leaves. And that's what I needed to show. So that's my inductive case. Okay, so we proved a property about the binary tree here. And the interesting thing here is that we get these two inductive hypotheses, one for each of the recursive invocations of the tree type. Okay, good. Have a drink of water. So, now let's look at one last complication that can come up. So, some of you may have heard of a rose tree before. Last time I asked this question, last time in the course, not that many people had seen them before, which kind of surprised me. But they're not that complicated. They're essentially just a tree that could have any number of children in any node. So instead of a binary tree, which always has 2 children for every non-empty node, so it's either 2 or 0 children, a rose tree has any number of children. Could be 0, could be 1, could be 2, could be many more, right? And it doesn't have to be the same number of children in every node. Different nodes can have different numbers of children. It's all fine. So the way we define a rose tree in Haskell is with 2 separate data types. So a rose tree itself, or firstly we have a forest data type, forest A, and A is just the type of the data as before, and it's essentially a list, right? We have an empty case and a cons case, which contains a rose tree of A's and another forest, right? So it's effectively a list of rows A. And rows A is a node that contains a value, a data type, which is our element, our data inside our tree, and a forest of children, right, for that node. So forest mentions rows, and rows mentions forest. So we can have 2 data types that are mutually recursive in this way in Haskell, and it works just fine. You can do the same thing with functions and with everything else. We can have stuff that is mutually recursive. So now let's define some functions on our rows tree data type. Firstly, we're going to define size and then height, and then we're going to try and prove a property. So let's go back to the whiteboard. All right. So let me just write down the data types so we don't forget. We have a forest of A's is either empty or a cons of a rows A and a forest of A's. And a rows tree is a node with an A and a forest. Okay, so there's our definition of the data types. So now let's define some functions. We first will define the size function. So size takes in a rows tree and gives me the number of elements in it. Size of node x children? Well, it's definitely 1 plus, but we don't have a way to get the size of the number of elements in a forest. So let's define a helper function, which I'll call size prime, to get the number of trees in a forest, or rather the number of elements, the number of values that we have stored inside the forest. So we pass in our forest there. And size prime, which I'll write here, takes in a forest of A's, gives back an int, size prime of empty. So we have two cases to deal with because we're dealing with these two. So we have size prime of empty is going to be 0, right? Obviously no elements there. And size prime of cons, t and t's, well, it's the sum of the number of elements in the rest of the forest with the number of elements in the rose tree t. So we can see once again we have size, which is defined in terms of size prime, and size prime defined in terms of size, right? So we can do this with functions as well. All right, next I want to define another function, which is the height. Height of rows A to int. So height here, given a node x c's, well, this contains an actual value. It's not possible for this node to be empty completely, so it's going to have 1 plus and then the height prime of c's. So far it looks a lot like size, right? We have height prime of, which takes a forest of A's, gives back an int, height prime of empty is 0, height prime of cons t's is, well, it's going to be the height of the tree t max the height prime of t's. So in Haskell, if you want to use a normal named function, not a symbolically named function, as an operator, you can put it around backticks like this, and you can use it in fix like that. But this is equivalent to writing, which is equivalent to, just as a note, maximum of height t and height c's, right? It's just another way of writing it. Okay, so there's our size and height functions. So if we just tried to prove the property that we wanted to prove, which is for all trees t, so our property is going to be, we're going to have this property p for trees. This is for rose trees. We want to show that height of t is less than or equal to the size of t. Now, if I try to do induction just on rose trees, then I would have, well, only one base case, because rose doesn't mention rows. It's just got a node with an A and a forest, so I just have to show this is true for node. So I'd have to show height of branch, sorry, not of branch, of node, and I've got an x and c's here, is less than size of node x and c's. But this wouldn't help me at all, because this is just going to be 1 plus height prime of c's and less than or equal to 1 plus size prime vertices. And that doesn't, and I can't make any progress there because I don't know anything about the relationship of height prime to size prime, right? I haven't proven anything like that. So then let's say, well, let's prove another property, Q, of a forest T's, which is that the height prime of T's is less than or equal to size prime of T's. So we got stuck over here. So let's try and prove the property we want for forests, for the prime diversions of all these functions, and then see if we can use that to finish off our proof for P here. So we'd have two cases here. So this one would have been a base case before. And if I have my property Q here, then I would have a base case where my T's is equal to empty. And then I would just need to show that the height prime of empty, which is 0, is less than or equal to the size prime of empty, which is 0 as well. So that's clearly true. And then I have an inductive case where T's is equal to cons K and K's, I'll call it. And what we want to show, we have an inductive hypothesis that height prime T's is less than or equal to, height prime of K's is less than or equal to size prime of K's. And what we have to show, I'm running out of space, so what I'll do is just condense this a little bit. So this is now 0 less than or equal to 0. That's that. And we can grab this and move it up like so. So now what I want to show is height of cons K's is less than or equal to, well, firstly we know the height of cons is equal to the maximum of the height of K and height prime of K's. And we have our inductive hypothesis that says that that's less than or equal to R. We only have an inductive hypothesis that says that height prime here is less than or equal to size prime. But we don't have an inductive hypothesis about height, right? What we want to know is this property P. And then if we knew both this current inductive hypothesis and this property P, then we could conclude that this is less than or equal to maximum of size prime K and size prime K's. Sorry, not size prime for the first one, just size. Right, that's what we want to do, but we don't have the inductive hypotheses to make that work. We don't know that height K is less than or equal to size K, because that requires me to prove property P, which I haven't proven yet, because in order to prove property P, I need to prove property Q. And in order to prove property Q, I need to prove property P. And this isn't really that unexpected, because I defined forest in terms of rows and rows in terms of forest. I defined size in terms of size prime and size prime in terms of size. I defined height in terms of height prime and height prime in terms of height. So my proof for the property P needs to be simultaneous with the proof of the property Q. So the way this works is a technique called simultaneous induction. Let me quickly go back to the slides. So to prove a property about two types that are defined in terms of each other like this, then we need to have a property P about all the rose trees, for example, and a property Q about all the forests, right? You need to have a property for each of the separate sets. And then you prove each of those properties just as though all of them were combined into one inductive set. So to illustrate what I mean, the base case that we have one base case for this simultaneous induction for our two properties, P and Q. We want to show Q for empty, right? That's the empty case that we get from here. And then all of the other two cases, the case for cons and the case for node, are both inductive. Why? Because cons mentions rose and forest, which are the two sets we're doing induction over simultaneously. And rose mentions forest, right? So they both mention one or more of the inductive data types that we're doing induction on. So we prove the property Q for empty, our base case. And then for the cons, we have an assumption, two inductive hypotheses. Our property P holds for the rose tree, and our property Q holds for the forest. And then we show that Q holds for the cons. And then for the node, we have another case here where we assume Q holds for our forest and show that P holds for the node with that forest in it. So let's do that now on the board. So we're nearly there. We've already got our definition of P and Q, but now we are equipped with a few more inductive hypotheses. So this is no longer a base case, this proof of P. Instead, this is now an inductive case, and we get an inductive hypothesis here. That is our property Q for the forest Cs. So inductive case where our T is node X Cs, and we have this inductive hypothesis that height prime of Cs is less than or equal to size prime of Cs. So if I use that, then that inductive hypothesis trivially solves, just by adding 1 to both sides of the inductive hypothesis, we get the goal that we're trying to show here. So by the inductive hypothesis, this one holds. And over on the side for Q, the base case for Q here is still the same. That doesn't change at all. But in the inductive case, we now have two inductive hypotheses. The second inductive hypothesis is the one that we already have about the forest, but we also have the inductive hypothesis, which is our property P for the rose tree K. So we say height of K is less than or equal to size of K. And by the same sort of weird maximum logic that we did before in the previous proof, we have now gotten to this condition here, the bottom line here, using our inductive hypothesis, and we can complete the proof now because we know that maximum is always smaller than or equal to the sum of two numbers. So because we can clearly see that there's no negatives here, so that's going to be smaller than or equal to size K plus size my pen is malfunctioning, size prime of K's, right? So if we take that all together, we can clearly see that this now shows that because this is equal to the size of cons, which I've run out of space to write down, but essentially this completes the proof. So we finish it off. Okay, so that's all I wanted to talk about today. I appreciate that this lecture is a bit half an hour shorter than the previous one, but I don't think that's much of a problem. Certainly interactivity in these lectures is a little bit reduced, so I do expect some of these videos to run a little bit shorter than normal, and that's fine. It'll give you more time to think about it. So after watching this lecture, the next thing I suggest you do is take a look at the tute. Make sure you've had a look at the questions before you go into the tute. In particular, the tute includes a couple of induction questions on lists, so be prepared with those for your tutor, and your tutor might ask you to go through them with the rest of the class. So that's all for today. Next week, we'll be looking at a system of reasoning called natural deduction and how we do induction in that system of reasoning. It's a technique called rule induction, which is kind of like a generalization of the structural induction we've done today. And we'll be applying that to language syntax, and we'll be getting back into programming languages. I appreciate this was mostly just about reasoning about Haskell, but I think it's a nice introduction to this kind of reasoning. Okay, see you in the next lecture.